Thank you. I'm in a difficult position. Unfortunately, a head of our clan, Boris Ryabko, could not come here because he met serious problems with his passport. So he passed his greetings to all colleagues and I should give this talk, and what should I tell you? That the main results of our talk are theorems, and I can only understand something like a dog, but I cannot speak about this. Alternatively, I can act like a flight attendant who gives you explanation of how life jackets work. And fortunately, the next speaker, Daniel Rybko, is here, and he is a pure mathematician, and he can answer all your questions about mathematics. So please do not hesitate. Ask your question from all parts of this talk.
But we are very interested in animal behavior, probably even more than theorems. So feel free to
yes, I told Boris about that, but he pushed me to talk about theorems. But I think that my work has done because I pushed him to prove them. So I did it. And a slight change with title, so integration of ideas and so on with application to animal behavior. Oh, sorry. And oh yes, thank you. So a new approach is suggested which allows to combine the advantages of methods based on Kolmogorov complexity with classical methods of testing statistical hypotheses. As distinct from other approaches to analysis of sequences by means of Kolmogorov complexity, we stay within the framework of mathematical statistics. As examples, we consider behavioral sequences of animals as logical texts, and we consider two examples: territorial behavior of gulls, the seabirds, and hunting behavior in ants. The idea of quantitative evaluation of complexity of sequences of symbols from a finite alphabet or texts is important for many scientific fields, including molecular biology, linguistics, zoosemiotics, and ethology. The degree of complexity of a text could be estimated by its Kolmogorov complexity. Although Kolmogorov complexity is not algorithmically computable, it can be, in a certain sense, estimated by means of data compressors. This simple observation has been a basis of many applications of Kolmogorov complexity to comparative analysis of many literary, musical, and biological texts. See, for example, works of Vitani. However, this approach does not give a possibility to use methods of mathematical statistics and, in particular, hypothesis testing. This is a severe limitation for the applicability of ideas of Kolmogorov complexity to natural sciences, in particular to biological studies. Indeed, since Fisher's classic works, its guru for biologists since his classic work from 1925, mathematical statistics and in particular hypothesis testing became the main method of quantitative analysis of biological data. So we have the following situation. Biologists need statistical tests to argue about complexity of sequences, and the standard data compressors estimate Kolmogorov complexity argument does not lead to statistical tests. And we suggest could say Boris suggested an approach with this, which allows us to combine the advantages of methods based on Kolmogorov complexity with classical methods of testing statistical hypotheses. The goal here is to estimate the complexity of sequences of different kinds and to use these estimates to test hypotheses. This gives the possibility to make decisions on the basis of standard statistical tests. For example, two sets of sequences could describe the behavior of an animal in different situations, or behaviors of different animals and possibly different species of animals, and alternatively the sequences can be the DNA of two different species. The problem is to compare complexity of such sequences. Similar problems arise in many fields of biology and other sciences. First, we describe the scheme of the suggested approach. Let there be a sequence of letters from a finite alphabet A, and let phi be a data compressor. We denote the compressed sequences by phi x, its length, and define the complexity per letter as follows. Generally speaking, we suggest to use the key of phi for hypothesis testing. It turns out that under certain conditions, the proposed approach can be used to evaluate hypotheses about the Kolmogorov complexity of the considered sequences, even though it is impossible to calculate Kolmogorov complexity. So the conditions. The considered sequences are generated by stationary ergodic sources, and the data compressor phi is a universal code. Informally, a universal code can compress a sequence up to its Shannon entropy per letter if the sequence is generated by a stationary ergodic source. Nowadays, there are many efficient universal codes which are described in numerous papers. It is important for practical applications that modern data compressors are based on universal codes. The following theorem gives a theoretical basis for suggested approach. Let there be a stationary ergodic source generated letters from a finite alphabet and a universal code phi. Then with probability 1 we have the same equation where the sequence x1 to xt is generated by the source and key from x1 to xt is the Kolmogorov complexity. The main idea of the suggested approach is very simple. Apply a universal code phi to estimate the Kolmogorov complexity of a word x1 to xt. Then use statistical tests to study this ratio. And in the same manner as one would study any other natural parameter, such as the weight, length, speed, etc. Given two sets of sequences V and B, our goal is to find a statistical test that can distinguish between the following two hypotheses. H0, the sequences from both sets are generated by one source, and H1, the sequences from the different sets are generated by stationary and ergodic sources with different Kolmogorov complexities per letter of generated sequences. In order to construct the test for H0 against H1, we consider an auxiliary hypothesis H1 star. The estimation of the average complexity is not equally large for sequences from different sets V and B. The suggested test T prime phi for H0 against H1, but not H1 star, uses a universal code phi and a consistent test T for assessing whether two independent samples of observations have equally large values. Say the Mann-Whitney-Wilcoxon U test. This is this what can I understand? The test T prime phi is as follows. First, calculate the average Kolmogorov complexity for all sequences from V and B, and then apply T for testing H0 against H1 star based on the new test, on the new sets. The following theorem describes properties of T phi prime. So the theorem is the type 1 error of the test T phi prime is not greater than alpha, and if minimum BV goes to infinity and the next minimum also goes to infinity, the probability to accept H0 instead of H1, the sequences from the different sets are generated by stationary and ergodic sources with different Kolmogorov complexity per letter goes to 0. And now I am on my land again, and as examples we consider astrological tests, texts of two kinds: territorial behavior of gulls and hunting behavior of ants. In the first case, we found that the complexity of territorial behavior in gulls differ in two situations: when a trespasser or an intruder approaches a resident's nest, and when it escapes from a resident's defended territory. I will show you a short film so you can see how it works in nature. And in the second case, we studied very small creatures, very small ants, and we found the complete successful hunting stereotypes in members of a natural ant colony are characterized by smaller complexity than incomplete hunting stereotypes in naive laboratory rat ants. And I will begin from ants. This is the first the second example of our studying is how ants hunt. Here are stages of their hunting stereotypes, and they hunt to creatures which are smaller than ants, and they can jump. So ants attacks the ant attacks the prey, bend the abdomen and head to the thorax, jumps to its victim, a springtail, and sting. And we compared behaviors of two groups of ants, members of a natural colony left, which we call wild for brevity, and naive laboratory rat ants of age from 3 to 12 days. And we place ants one by one into a container with their potential victims, and made our video records, and then we analyzed our records by Nodus observer systems. So I would like to show you how does it look. Can you see how an ant caught its
I
victim.
think we have seen an ant, but
Yes, yes,
where are
yes.
the others?
And
Oh,
yes, yes, yes.
But what are these pieces of glass around all
It's modeling. We were modeling grass by transparent bottles, water bottles. And and where is my presentation? This one, thank you. But the whole directory. No. I mean a whole directory.
The what? Sorry.
directory with
Directory.
other
Okay,
files.
directory.
I see now. Thank you. And this is more interesting. You can see a naive laboratory rat ant who is friendly touching his potential victim. Like some cats raid at home and failing to catch a mouse. But it is interesting that some naive ants possess catching stereotyped behavior, hunting behavior stereotyped as once as entirely, and so there are some naive born hunters within a family. And note that ants of this and many other species are not genetically equal. They are very genetically variable. So they are not twins within a nest. And you can see how it friendly touches a potential victim, and it does not demonstrate its hunting stereotype.
But finally he can't.
No.
He just looked like this.
Why is his butt glowing?
So we represented behavioral sequences as texts in which behavioral units, 10 in total, singled out from video records and denoted by symbols, letters, served as an alphabet, such as waiting, slow walking, running, turning around, bridging, posture, attack, capturing the prey, kicking the victim with a sting, and transporting the prey. And we analyzed our video records, and what it is important to note is that we use long texts consisted of many repeated symbols. We had selected 10 behaviors denoted by 10 symbols, and within them we can see completed successful hunting behaviors such as this, and also incomplete behavior which was not ended with catching the prey. So we summarized text files, and we had many incomplete and many complete stereotypes, and then we used the archive for comparing sequences of the equal lengths, and we compared the compression ratio. So we tested the hypothesis H0. The sequences from two sets are generated by one source against H1. The complexity of sequences from one set is on average larger than the complexity of sequences from the other by the Mann-Whitney-Wilcoxon tests. And it turned out that files corresponding to the successful hunting stereotypes compress better than those corresponding to incomplete hunting stereotypes, both in wild and naive ends. Moreover, H0 is rejected with alpha 0.05, and we can conclude that on average the complexity of sequences from the first set is larger than in the second. In sum, this data support our suggestion that complete successful hunting stereotypes in ends are less complex, and we think that it is because they are less redundant and they contain less noise, less additional not significant acts. Yes.
But then you write that the successful hunting stereotypes compress better.
Yes.
That means that they are less complex.
Yes.
But isn't the wild ones that are more successful in hunting?
Yes.
And then you say that the wild ones.
Yes, but as I already told, there are some naive ants who possess this stereotype from their very early stage, and they are born hunters. So we include born hunters from naive ants and successful hunters from wild. Their sequences will be compressed equally. And this is somehow the nature-nurture problem, not only for ants. The nature-nurture problem is wide known, and it is painful for human parents. Are very excited to decide whether their child has innate prone to be a violinist, whether it is a born musician. So it is a very exciting problem for human, but for animals it is also not so simple, because we can see how cheetah and other cats teach their children, and how birds teach their children to catch and open shells, but it is not so simple, because as many recent data have demonstrated, there are no dialogues between children and mothers, or children and parents. These are rather monologues, and the innate behavior is also very important together with teaching. So it is a great problem for biologists and for ethologists in particular to distinguish between innate and learned behavior. I should hurry up with my talk, and I only can say that it becomes possible for ethologists to extract innate behavioral patterns by comparing behavioral sequences of different levels of complexity without resorting to rearing naive animals. And it is a very important tool for biologists. And our second example concerns territorial behavior in gulls. You can see an alive bird and an intruder or mook gull that is approaching to resident nest. So we compared two behavioral sequences, how a gull behaves when an intruder is approaching and how it behaves when it goes away. And I would like to show you how this works. So you can see how a mook gull is approaching, and a host of a nest who is clutching eggs, sitting on eggs, is a little bit nervous, and it demonstrates go away, go away. So we can represent its behavior as letters, and we selected 60 distinct behaviors. So we are removing the intruder. And you can see how different these sequences. And we compose a dictionary of gulls' territorial behavior. And as I already told, we used 60 behavioral units, and it turned out that the files corresponding to the reactions of resident gulls towards the escaping intruder compress better than those corresponding to birds' reactions towards the approaching and staying intruder. And this data suggests that reactions of a resident gull towards an approaching trespasser are more variable and chaotic than its reactions towards the escaping one. Oh yes, this is the last slide. Thank you. And in conclusion, I would like to demonstrate my book, also published here in Cambridge 5 years ago. But in this book you can read lots of interesting things about animal intelligence, but there are many problems of analyzing of animal behavior which had not been solved until now. So applied to different animals, the proposed methods is a promising tool for distinguishing between basic typical behavior patterns and flexible behavior. And more generally, the methods provides a statistically sound tool for reasoning about Kolmogorov complexity of biological texts. This is a potentially of great importance in many branches of biology. Thank you for your attention.
Other questions?
It's more a comment than a question. But it seems that it's very easy looking at this. The behaviors are really significantly different, just by the simple fact that, for example, ant either kills this strange thing or doesn't kill it. So the idea to use Kolmogorov complexity to distinguish between them looks completely redundant. You can easily distinguish without any Kolmogorov complexity. So it seems like there is a kind of interesting biological experiment, but the Kolmogorov complexity doesn't really help at all. You just have the simple, you obscure this experiment by speaking about Kolmogorov complexity, this entropy statistical test, and so on. It's obvious that these things go from different sources. The behavior, and
I do not agree indeed, because we choose the mainly demonstrative, pedagogically easier demonstrative examples, and the main results of our talk are theorems, not applications this method to other species of animals, more and more species. So I think that maybe we chose two demonstrative examples, too impressive, but
much more
yes,
easy
yes,
than the
yes,
theorems. Theorems are more or less obvious.
But what can I answer in this case? And that is, if we remove the last element of its behavior, kill instinct, and we also can compare these sequences and can apply Kolmogorov complexity and compare how they compress, and I think that we can find a limit under which we can judge about innate and learned behavior, and we are working on this right now. So next time I will demonstrate more slightly distinguishable behaviors, I think.
I think you should forget about complexity.
Okay.
Work really on the randomness.
I can't forget, yes.
I have a comment, sorry, that is kind of similar. I mean, the work of Vitani and Zalessky was far more general. This is just a particular case. So what they did is they had a lot of sequences and they classified them in terms of Kolmogorov complexity distance, and they could see like which is exactly the structure, like the evolutionary structure. So here you're just taking two sets of sequences and just taking the average Kolmogorov complexity and checking that. I mean, it looks like too
It's
much
like
of a
distinguishing
simplification. I mean, it's
DNA sequences from
Yeah.
MIDI files in
so it's like,
cerebracity.
yeah. So in those cases,
That's-
what they do is they take a lot of sequences and they do a whole classification. So they kind of reconstruct the evolutionary history. So if you wanted to, I mean, if you had two sets of sequences like you do, and you use their method, you would very clearly get very different structures. So you would very clearly see that they don't correspond to the same phenomenon. So, I mean, your statistical test could be much more, how do you say, significative than just, checking average Kolmogorov complexity, which seems like, I mean, I don't see any theorem actually. I mean, I see that the theorem was already proven by them in the sense of the deep theorems having to do with information distance. But I expected something else actually. I'm a bit disappointed.
So maybe I can answer about
Yes.
that because it's more about mathematics. I'm not an author, but I can answer to this because the main difference with Vitani box is that Vitani box gives you some information about the Kolmogorov complexity mainly, but it doesn't give you the statistical test that would say that type 1 error is, say, at least at most alpha, and type 2 error goes to 0. They do not give this.
No, but the
No,
theorem
but
actually
it's a
is
sequence.
essentially that both things converge to both Kolmogorov complexity and the compressed size converge to entropy of the source. And this is true since it's universal compression. So theorem is really
No, that's the first theorem that they use. I mean, I agree that the theorems are quite simple, but the first thing that they use is that this thing converges, right? But then they also construct confidence intervals. So
okay. But since there is no assumption about the difference in complexity, this confidence interval just abstract convergence to 0. It doesn't mean anything.
No, so the type 1 error, you can fix it to be alpha for any method.
Of course, but
type
the
2,
other is not bound.
The other one would go to zero.
I think as we should not, we like Kolmogorov complexity all, but we should not disturb the biologist with this if it's not necessary. Let them do the really interesting thing, not worrying about the statistical tests and alpha and beta and this entropy. It's answer much more interesting. No, really in the experiments, for example, when you try to find your classical and still doubtful, I think people don't believe them, experiments when the ant finds path in a maze.
But people already believe.
Not all.
Okay,
Not all, of course, but not all believe even in Frisch experiments.
Okay, but
that's probably the discussion.
So with Carl von Frisch, we are in the same club. Okay.
The first experiment was serious.
But we have more than 1 hour to discuss that. Thank you.